Hi guys, welcome back to 100 Days Machine Learning Crash Course. Today is the last session of the third part, which is the part of deep learning. So congratulations to made it through here. So in the last session, we want to see some examples of GAN and variational autoencoder and in Keras. So because this is so important to be able to implement these kind of networks in TensorFlow and Keras. So first we will see some examples for GAN. Okay, so there is a really good GitHub link, as you could see in here, and in this repository there are lots of different GANs implemented to you could just use them and see how they works. For example, in here we have GAN, CGAN, which is conditional GAN, which we want to see these two in this session. And also there are lots of other GANs that are pretty popular, like Pix-to-Pix GAN, DC GAN, and others. In here I just copied the code for GAN. So first we want to see the code of GAN and realize how it works. So I just copy that code into my Jupyter notebook. So okay, so if you remembered, in GANs or generative adversarial networks, we have two different networks. So the first one is generator and the second one is discriminator. So the generator tries to generate some realistic samples from some noise, realistic samples or realistic images, and the discriminator tries to discriminate between the realistic samples or it is better to say training samples or real samples, and these generated samples that are generated by our generator. Okay, so we have a two-player game, if you remember that, in GAN. So let's see how to implement that in Keras. Okay, so as you could see, first we have some import of different layers which you probably know about them. We have the optimizer Atom, and also we have the sequential model because we just want to use the sequential model in this example. Okay, so let's see what is in main. Okay, so in main we create an instance from the GAN class, and after that call the train on that. Okay, so let's see what is the train. Okay, so in train, as you could see, we first load the MNIST dataset. So we want to train our network or our generator network to create some images that are different numbers. So we want to generate new digits, new handwritten digits by learning the MNIST distribution. Okay, so first we load the data. So we know how to load the data with Keras, and after that we scale the training data in the range of -1 to 1. So this is kind of normalization. And after that we just reshape that, or if you remember, the input for the networks should be something like this. So we have number of samples, we have 8 widths and the number of channels. So in here we have grayscale image, so the C should be 1. Okay, so we add, because the training X is something like this. Now we use expand dims to just convert it to this tensor shape and add an extra one dimension to the last dimension. Okay. Okay, so after that we have we should create the labels for the discriminator. So now, if you remember that for training this GAN, we should first in an iterative manner, we should first train discriminator for one iteration or for one batch, and after that train the generator, and after that again for discriminator, and so on. Okay, so in here we create some labels for the training images, and we create some labels which should be 0 for the generator images or for fake images. So because for training the discriminator, we have kind of supervised learning, so we should have some labels to train the discriminator. So for the images that come from the training distribution, we label them as 1, and for the samples that comes from generator, we label them as a 0. So we just create the labels from the NumPy, and as you could see, we create the 1s for the valid or for training images, and create 0 for fake or generator images. Okay, so now for different epochs, we should we first train the discriminator. So we randomly select or generate some indices first, and after that select a batch of from the training data, and also so we should create a noise, a random noise, and create some fake images with the generator. So we have generated images. We should use the generator network to generate some fake images. So we store them in gen images. Now we should train the discriminator with these real images and with these fake images. So we could do this in just 2 different lines. So first for the valid or for real images, we train the discriminator on one batch. The batch has the images, and the labels of the images are 1 because all of them are true images. And after that we train the discriminator on fake images. So we have the generated images, and the labels of them are 0. So but instead of that, you could actually append images and generated images, and also append valid labels and fake labels, and after that just train the discriminator in 1 line. But also you could do that in 2 lines, as you could see in here. And for getting the loss function of your discriminator, just taking as you could see, calculating the mean of these losses. Okay, so now we trained the discriminator. Now we should train the generator. To train the generator, we should fix the discriminator weights, right? So this part maybe is a little tricky, so you should actually pay a little attention to this part. So for training the generator, we create some random noise. After that, we train the combined model with some noise, but because the generator wants to fool the discriminator, we should pass the one labels to this discriminator. Okay, so because the generator wants to fool the discriminator. Let's see what is combined model. Okay, so the combined model is actually, so let's see in here we have the discriminator. We built the discriminator. So let's see, the discriminator is a simple neural network. So this is the discriminator, and also here we have the generator. Also, this is a simple neural network. So we have the generator in here, and we also build the discriminator. And when we want to train the generator, we should train that through the discriminator, right? So let's see, this is the generator and this is the discriminator. When we want to train this generator, we should train this generator through this pass. We could not train this directly, so we should use the combined model, but we should fix the weights of the discriminator. And also, because we want the generator to fool the discriminator, we label the fake images as 1. Okay, so to make the discriminator weights fix, we use the trainable attribute from the discriminator and make it false to fix the weights of the discriminator. And after that, we just combine, we create a model that is the combination of the discriminator and generator. So this combined model takes the random noise as the input, and as the output has 1 or 0, which shows that whether an input is fake or not. Okay. Okay, so and now we just train the generator through this combined model. And for generating samples, as you could see, we just generate some noise, and after that we use the generator to generate some new samples and rescale that to plot them. I ran this model, and as you could see, we have the training procedure, and here is the training. In fact, here is the samples that are generated by the generator through different epochs. So as you could see here, first the generator images are just not good at all. After that, we have maybe a better or more clear thing, and as we goes on, we could see that we have more definite digits. So now let's see, when we go enough iterations, let's see what is the end of that. So okay, so as you could see, we have a very good quality images in here. And just note that this network is not convolutional. So you could use DC-GAN or see the DC-GAN architecture to use convolution layers in the generator, but this network is just a simple MLP. So by this fact, the generated images are pretty genuine for this task. So these are completely new images, and these are not in the MNIST dataset, and so these are new digits. And you could use them to train your CNN. So if you want to train a CNN to recognize digits, you could train that on MNIST and on these generated images from the GAN. Okay, so this is the GAN. Now let's see the conditional GAN that we talked about it. That is very similar to the GAN itself, but we should just pass the label to the generator and the combined model. So we just examine that through the GitHub. Okay. So to have a conditional GAN, we have a label, and let's see, so we have noise as the input and label. Okay, so because we want to have, let's draw the model in here. So in conditional GAN, currently without conditional GAN, as you could see in here, we cannot control the number of the generated digit in here. So when we create a noise after the generator, it could be 9, it could be 3. We don't have a control over it. To make it controllable, we should create conditional GAN. So in conditional GAN or CGAN, the generator has two inputs. So the first one is noise, or let's call it C, and we have a label, okay, which is, let's call it C, to generate new images. So if we have a noise with and we want to have 1 in the output, we should pass to 1 to this C and append those together to generate 1, okay, and so on. So the generator image, where is that? Okay, the generator image has, and combined model has, 2 inputs, noise and label, and so the training is pretty similar to the GAN itself, but we just also pass the labels to train the discriminator and the combined model or the generator. Okay, so in this case we could generate some new, let's run it. Maybe it is good to run this also. So we go to the raw, and so as you could see here, the training process will be start. Okay, good. So at first, as you could see, we have just noise, and when we train the network for more iterations, then we have more definite images. Now let's see, for I think 1000 iterations is enough to have more definite or discernible outputs. So this is for 600. Now we could actually recognize 0 or 2 and also maybe 3. Okay, now we have 0, maybe 1, I'm not sure about it, but we have 3, 4, 6, 7, and also maybe somehow 9 if you have a very good vision. Okay, now this is, I think, is fine, but actually definitely you could train this network for more iterations to get better results. Okay, so now we have a conditional GAN. So by passing the label that we want, we could generate the digits that that is desired. So when we pass 0 to the network, to the generator, it creates 0 digit as the output, and so on. So this is so cool. Okay, now let's see. Okay, just let's stop it in here. And now let's see the variational autoencoder in Keras. So it is an example from the Keras itself. So let's start from here. This is a variational autoencoder example on MNIST. So we load the MNIST dataset, and after that we reshape it again and normalize it. And so the VAE model, let's see in here, the VAE model, if you forget it, the VAE model has 2 parts, the encoder and the decoder part. And so this is the VAE model, and if you remembered, we used the reparameterization trick to be able to pass the gradient through here. Okay, because this sampling make it impossible to flowing the gradient through this pass, but by using a reparameterization trick, we now we are able to just train the network properly. Okay, so let's see in here. First, we build the encoder. So we have an input, and it has just only one layer as the intermediate layer, and for the output it has a mean and variance, okay, as the latent with the latent dimensions. And now as you could see in the comment, so it uses reparameterization trick to make the gradient flow possible. So after that we have the encoder model, which has some inputs, and the output is the mean and variance, and the z as the output, which are in fact the latent variables, or as you remember, these are the encoded features. Okay, so this is the encoder. So for decoder, the decoder wants to decode the latent space, so the input of the decoder is the latent inputs, and the output of that is the original dimension of the image. For example, if it is MNIST, then we have 28 by 28 dimension in here. So we have the decoder model, and the VAE model is the stacking just the inputs and outputs. So the outputs is, in fact, we have the decoder model. The decoder model wants to decode the inputs that are encoded by the encoder. So this is the VAE output. So we have the VAE model in here. Now let's see in here we have the reconstruction loss. So if we use MSE as the reconstruction loss, so the reconstruction loss was for decoder part. So we have the MSE, we could have the MSE as the decoder part to have images that are close to mean. So we have reconstruction loss, and also we have KL loss for the encoder. So let's again see here. So now we have if you remembered, we derived a lower bound for likelihood maximization, or for maximizing likelihood, and we call it elbow. And so this part was related to the reconstruction, and we had another term for the encoder part. So now we should, let's see again here, now we have the part of the decoder or the reconstruction. So we should have also the part of the encoder loss. Okay, so we create the KL loss for encoder, and the VAE loss, or for the loss for stacking the models, will be the mean of the reconstruction and KL loss. Okay, and after that we just train the network and plot the result. But currently maybe the GAN is much more popular than VAE, as I mentioned, and VAE maybe is better for research purpose. It has lots of things to do in VAEs to make them more usable, to generate some samples that are similar to GANs. Also in GANs there are some different defects of GAN that we talked about them, but I highly recommend to look at these this repository in GitHub. Especially the WGAN is one of the most maybe improved versions of the GANs to stabilize the training process of the generative adversarial networks. So I highly recommend to take a look at this, and also you could actually read the paper of WGAN to just read more about it. So I think these are very necessary if you want to work in this area. Maybe there has some mathematics difficulties for you, but don't worry about them too much. So if you want to research in GANs, you should improve your math skills in probability and statistics. So start with more easy papers, and then try to read more advanced papers and difficult papers. Okay, I hope that you enjoyed from all of these parts of the learning process, from the traditional methods to here, which is deep learning. And just let me know if you have any comments or feedbacks. Just reach me out, and then let me know. I would be happy to answer you if you have any questions. So I hope to see you in maybe in other place, or maybe some other course. So hope to see you again. Bye.